So this is the webinar organized by LearnCX. The webinar is focused on introduction to reacting flow modeling using CFD, and this is the first part of this webinar, as the topic is quite extensive. We have divided it into two parts. First part will focus on reviewing the fundamentals and theory related to reacting flows as well as modeling of reacting flow, and the second part will focus more on the modeling concepts as well as application side of CFD on the reacting flow. So this is an introduction to reacting flow modeling using CFD, and we will begin this discussion now. The roadmap for this session is, first we'll have a introduction to all the participants, and after that we will begin the webinar presentation. The webinar presentation ends with questions which we'll take from your side and try to answer them here. You can post them in the chat box during the session also, and in the end we'll have closing during which we'll brief you about our activities as well as the courses that we offer. So firstly, before we begin, thank you for your registration and attending this particular session, taking time out for attending this particular webinar. And this is an introductory webinar on reacting flow modeling. This is the 7th webinar in a series of webinars which will be conducted by LearnCX. We will continue to conduct much more free webinars in future as well. And this webinar is designed to act as an introduction to reacting flow modeling process within CFD. So this will give you overview of the reacting flow modeling process, but as this webinar is divided into two parts, in this particular session we will only discuss fundamentals related to reacting flows. About LearnCX, we are actually a training initiative or training division of Center for Computational Technologies Private Limited, situated in Pune, India. We look after all sorts of training activities related to CFD as well as CAD. And we have an online training course module which actually helps participants to learn complex technologies at their own time and place, and at their own pace, learning pace that they can afford. So our training courses are available entirely online. So that was information about what we are and what we do, and let us begin the technical session of this particular webinar with an overview of what is to follow in the slides to come. So first is we will see why reactions at all matter to us, why reacting flow is at all important in order to analyze or study. After that we will have fundamentals, that is we will discuss fundamental or review the fundamental concepts related to chemistry and reacting flow. Then we will see concepts related to modeling reacting flows, what is the modeling approach and what sort of models are incorporated. And in the end we will have summary where we will summarize what we have learned in this particular webinar. So the basic question that arises is why it is at all necessary to model or to study reacting flows. So if we observe things around us, we see that reactions are present everywhere, whether it is actually in a reactor plant or in a chemical reactor, or even a simple candle burning, it is a reaction, a combustion reaction. Even power plants generate energy based on reactions, as well as a wood or coal which is burning is a combustion reaction. Even the propulsion within the propulsion system reactions are present, as well as jet engines run on reactions. Even a simple stove where we cook in kitchen, it is a combustion reaction. Even the cars which operate by standard combustion engines, they run because of the reactions, as well as even the new alternative energy operated cars which operate on battery as well as fuel cell concepts is basically driven by chemical reactions. So wherever we see around us, things are basically operating or running or generating energy because of chemical reactions. So this entire world runs mainly because of energy generated from chemical reactions, which is combustion forms a major part of chemical reactions which generate energy. So whether we take a car, helicopter, aircraft, heater, barbecue that we usually enjoy at our home, or lighter, or even simple gas in the kitchen, and industrial furnaces, bigger reactors or power plants, and wood fire, and we can go on and give many more examples of reactions which run the world around us. So the energy that we consume, and because of the energy that the world operates, is generated from some sort of reaction. So that is why it is necessary to design operations or design systems where reactions are taking place, so that we can make them more efficient. Also we can reduce the pollutions that is created because of chemical reactions, and also utilize the energy in a better way and in a much more efficient way. So in order to study any type of reacting flow, it is important to understand or review fundamentals associated with chemical reactions. So a chemical reaction is defined as a process that leads to transformation of one set of chemical substance into another. So it is just a change in chemical substance produced by chemical reactions. An example sort of combustion reaction shown here, and chemistry or reactions were originated by a renowned scientist coming up with a theory for combustion as a chemical reaction with oxygen. So that is a sort of a historical perspective. There are various types of reactions starting from different mechanisms which the reactions operate on. Some of the basic types are listed here. First is synthesis, which defines as a reaction in which two substances combine and form a combined single substance, where A combines with the B and forms a sort of a substance AB. Decomposition, where A and B separate when they were together first and they separate into two distinct substances. Even a single replacement reaction in which A and B as a substance which is combined, it reacts with C, the third substance, and there is a replacement of a substance and we form AC as a single substance and B is separated out. And there is a double replacement where both the substances are replaced or they separate out to form completely new two substances, which are combination of two original substances. So this is a sort of a 4 different types of reaction based on what sort of mechanisms take place, and it is usually a convention that the substances which are part of initial reaction mixture are referred to as reactants, and the final substances which are formed after the reaction takes place are referred to as products. So this comes from basic understanding of chemistry. And there are also exothermic reactions which emit energy, and endothermic reactions which absorb energy. So a concept that is very much associated with chemical reactions is mole fraction. Whenever we consider chemical reactions, most of the chemical reactions are basically having mixture of chemical species. So it is important to identify each individual chemical species contribution. So therefore these concepts have come into origin. So mole fraction is defined as fraction of total number of moles of chemical species in a mixture of chemical species. So it is somewhat defined as number of moles of that species divided by total number of moles. Also mass fraction, which is a related concept, it is the fraction of mass of a chemical species in a mixture of chemical species, and it is again defined as a ratio of mass of that species upon total mass of the mixture. Now the relation is pretty evident. The relation between mole fraction and mass fraction is that mole fraction is related to mass fraction. Mass fraction is related to mole fraction, where we multiply the mole fraction by molecular weight of that particular single chemical species divided by the molecular weight of the entire mixture, where we define the molecular weight of the mixture as summation of individual molecular weight multiplied by the mole fraction of that individual species. So that is a sort of a understanding of how to make quantitative contributions of individual chemical species in a mixture of chemical species. Now whenever we say that there is a sort of chemical reaction, we evidently talk about mass transfer of chemical species, which usually has two components. First is convection and second is diffusion. So diffusion takes place from higher concentration to lower concentration, and convection basically needs a somewhat medium necessary in order to carry the mass transfer mechanism. And there is also something called as thermal diffusion and barodiffusion. Thermal diffusion is mainly because of temperature gradients. There is a diffusion of chemical species because of temperature gradient, and barodiffusion is because of pressure gradients. So individual chemical species always tend to diffuse when they are present in mixture, and we need information of what sort of diffusion mechanism and rate that they follow, which is given by diffusion coefficient. Various methods are used to calculate diffusion coefficient. You can take it as a constant or compute it from binary mixture type of mechanism and mole fraction, and you can also use interkinetic theory in order to calculate diffusion coefficient. If turbulent flow is present, then diffusion due to turbulence dominates all other laminar or other type of diffusion mechanisms. So let us come and discuss some very familiar term which is called as stoichiometry. So stoichiometry is basically an idealized reaction mechanism that can be followed, and which means that if we have a combustion of CH4 with air, usually a stoichiometric balanced reaction requires 1 mole of CH4 for 2 moles of O2. This is a stoichiometric reaction. and if we have less or more number of more moles of CH4 for 2 moles of O2, it deviates from stoichiometric balance of reaction. So in that case we have different type of products or different type of a different outcome of those reactions that can be present. So in case we have less number less number of CH4 that is present, we have lean type of mixture, and if we have more than stoichiometric required CH4 present, we say that it is a rich mixture. Usually whenever we have that sort of reaction, the hydrocarbon substance is called as fuel, and the air with which it is reacting, mostly it is called as an oxidizer, or so that is a sort of terminology that is utilized. So if the fuel is less than stoichiometric fuel, then it is called as lean mixture, and if the fuel is more than stoichiometric fuel, it is called as rich mixture. How do we define the outcome when it is lean or rich mixture? Usually what happens is if it is a lean mixture, you will have more the products will have unused oxidizer or unused oxygen which is left. So oxygen, if we have lean mixture, oxygen will be left because it is actually more than required oxidizer is present. And if we have rich mixture, then we will have hydrocarbons as an outcome, and this can produce pollution as well as unburned hydrocarbons which are left. So this is the sort of outcome that is present if we have lean or rich mixture. Coming to another term which is known as equivalence ratio. Equivalence ratio is basically comes from stoichiometric concept, which means air to fuel ratio. So if air to fuel ratio is considered, equivalence ratio is defined as the ratio of air to fuel ratio in a stoichiometric balanced reaction divided by air to fuel ratio which is actually present. So this is a sort of equivalence ratio, and which again gives us a sort of a trend or sort of understanding of if the equivalence ratio is greater than 1, we say that it is actually a rich mixture which can result in polluting emissions and incomplete reactions, whereas if it is lean mixture, it will result in no emissions, but it will result in excessive oxidizer usage. So that also we have to be careful about. So this is something called as excess air, because more than required air or oxidizer is present. Going back to our earlier discussions, since we have discussed concepts related to reactions, now we will move on and discuss some fundamental concepts related to reacting flows and the modeling approaches associated with reacting flows. So when we say that the term reacting flow, it involves a very broad range of physical phenomena, starting from chemistry up to turbulence and much more deeper coupled physics. And for modeling reacting flows, we have to model a set of partial differential equations. Those equations are time-dependent coupled partial differential equations which govern the conservation of mass, momentum, species density, and energy. All these phenomena coupled together. So the partial differential equations which we are going to model describe the motion of fluid. They also incorporate chemical reactions, mass transport, and other heat transfer related concepts like heat transfer, radiation, as well as molecular diffusion. So if we couple all these phenomena together, we also have to cater for mass transfer because of fluid related phenomena like convection. So quantities such as density, velocity, energy, which are smoothly varying functions of positions, they come under convective type of mass transfer because of convection effects, and these are represented in the partial differential equations by fluxes of conserved quantities. So that is coupled together with chemical reactions, which are actually put into the model by representing them as a production term or loss term of mass species or chemical species, and the species conservation equation are solved separately than the momentum equations. Also we have diffusion, which is represented by a divergence flux, and changes in energy due to molecular diffusion and chemical reactions are accounted by giving in a heat flux into the energy equation. And if we have to consider complex physics like radiation, that is again represented in the energy equation as a source term, and separate models are solved for radiation. If there is combustion presence and we have wave phenomena, it is described in the reacting flow by solving separate governing equations which are coupled with the continuity equations. So all these methods or all these mechanisms are put into a coupled set of partial differential equations which are solved. Chemical reactions, which can be unimolecular or bimolecular, the reactions take place as a mixture species, and we define them by solving the rate of reactions. So there has to be a mechanism in order to cater for rate of reactions also, and that has to be incorporated as an ordinary differential equation, which is coupled together with the conservation equations that we are solving. And from these, the temperature is also calculated from the energy equation, and if the rate of reactions are dependent on temperature, a mechanism has to be solved for that. And the standard mechanism that is generally followed is Arrhenius rate of reaction, which we'll discuss in the coming slides. So this is if the reactions also absorb or emit energy, that is again taken into account by giving a source term into the conservation equations. So this is the sort of conservation equation solved for chemical species, which is the transport equation for chemical species, where we have Yi as the mass fraction of chemical species, and these are different terms which cater to different phenomena that we have just discussed. So Ui is actually defined as the fluid velocity, and d is the diffusion coefficient. And when we say Ri, it is actually the reaction source term. Because of reactions, the species can be added or absorbed, and that is this particular source term. And the rest of the S is basically additional, if there are any other source of chemical species, that is the S that incorporates it in the S term. So what happens here is basically this is the rate of change of chemical species, this is the rate of change due to convection, that is the fluid flow, that's why the U velocity is coming into picture, and this is the diffusion term, which is because of diffusion of chemical species from higher concentration to lower concentration, and this is the addition or subtraction of chemical species because of reaction, and this is the source term. All these terms put together is the conservation equation for chemical species, which is solved in addition to the momentum equation and continuity equation. So let us have a graphical overview or a pictorial overview or understanding of this particular reaction mechanism. Let's say we are solving a reacting flow. So what we need to, what sort of mechanisms or algorithms or models we need to incorporate in order to solve reacting flow? First is we have to put together chemistry of that particular reaction that we are modeling, or thermochemistry as we term it. In addition to that, we also must be aware of chemical kinetics, which is associated with that particular reaction. Species transport, that is creation or absorption of species because of chemical reaction. A transport equation is required for that, and all this thing coupled together along with the fluid mechanics of the flow. So this 4 elements put together forms a reacting flow model. So when we talk about chemistry, let's take an example of methane and air combustion. Then we will have the chemical equation, which is the stoichiometric equation, balanced together, which will give us the reactants and products. So that is put together, and it will give us the final and initial chemical species. But in addition to that, we also need to know what sort of rate of reaction is there. That means at which speed the chemistry proceeds, and if it needs a time, what sort of time this reaction needs in order to proceed, what is the reaction speed, as well as the difference between thermochemistry and chemical reaction that we need to understand. Thermochemistry deals with only the initial and final states, whereas it is totally independent of the speed at which one goes from the initial to final state. So thermochemistry is just the reaction, writing down the reaction, first initial products and initial reactants and final products, whereas the chemical kinetics is basically associated with how much time a reaction will take in order to proceed. So that both the mechanisms need to be put into the model. Chemical kinetics needs additional models. So this is the chemical kinetics model that usually is incorporated into the reacting flow model, which is the Arrhenius reaction rate, in which the reaction rate is also a function of the temperature that is present. So this is a ready-made reaction. So once we have, as we have discussed, for the chemical kinetics, we need an additional mechanism like the Arrhenius rate, which is put into the reacting flow model. Now let us shift a bit of the attention and focus on in detail about the how the chemistry is coupled with fluid flow. But the majority of reacting models have applications in combustion, so we have taken a sort of a approach where we will discuss combustion reactions henceforth. So basically combustion reactions have a strong coupling between the reaction as well as the fluid flow happening around, which is mostly turbulent. So when we say there is combustion happening, it can be a non-premix combustion where the fuel and oxidizer enters the reaction zone in distinct steam, whereas in case of premix systems, the reactants are mixed at the molecular levels before burning. So Non-premix combustion will have its own typical properties, like they will have separate streams for fuel and oxidizer. Convection or diffusion of reactants from either side into flame sheet will be there. Also turbulent eddies which will distort the laminar flame shape and enhance mixing. We will also this sort of a non-premixed combustion may be simplified to a mixing problem, whereas in premixed combustion, fuel and oxidizers are already mixed at molecular levels before the ignition, and there is cold reactants that are present which propagate into hot products. And also rate of propagation or the flame speed depends on the internal flame structure, and it is much more difficult to model this premixed combustion as compared to non-premixed combustion problems. Also the presence of turbulent creates additional complexities, and there is also something called as partially premixed combustion, in which reacting systems with both the non-premixed as well as premixed fuel oxidizer streams. So this is an overview of how reactions or combustion, to be specific, is categorized based on what sort of chemistry and fluid mixing methodology is followed, which we have 3 different distinct fluid mixing methodologies, which is non-premixed, premixed and partially premixed. So now this particular slide will give you an overview of modeling approach that is followed. So this is the last slide of this particular technical presentation. What we will this particular slide will give you also an overview of what will follow in the part 2, where we will discuss in detail some of the models that are present here and focus more on combustion reaction modeling and application of combustion. So if we have to model chemical reactions, we have to solve transport equations or incorporate transport equations into the reacting flow model, which are continuity equation, momentum equation, energy equation, and chemical species transport or governing equations. In addition to that, we also have turbulence which is present, and sometimes or most of the times the fuels that are present are in the form of solid particles or liquid droplets, which for which we also have to solve Lagrangian discrete phase models, which is coupled together with the transport equation. And it will in order to cater for turbulence, we also have to solve turbulent flow models. There are also real gas effects that needs to be incorporated in order to take care of properties variation. So all these things coupled together will actually give us the coupling between fluid flow and chemical reactions, and depending upon whether the reaction mechanism or reaction kinetics or chemical kinetics is what sort of speed it has. If we have infinitely fast chemical chemistry or chemical kinetics, we have a different set of models that has to be used. There is the reaction models, which will be eddy dissipation model, premixed model, non-premixed model, and partially premixed model. Whereas for finite rate chemistry, we will also have some set of models like laminar flamelet model and laminar finite rate model and composition PDF. Also these can be used in some part for infinite chemistry also. So depending upon what is the chemical kinetics, we can select either of the reacting flow models, and this takes care of the species conservation as well. And if there is incomplete combustion, we will also need to take care about the pollutant models, as well as if the temperature variation is large, we have to take care of radiation models. So as you can see an overview here, reacting flow modeling is all this combined together. So it is not a single model, it is actually a modeling approach. So when we say we have to model reacting flows, we have to take care of all these aspects and select among all these models and put together a CFD model in order to simulate our problem. So the details of this we will discuss in the part 2 of this webinar, and we will go into detail of all these aspects and also have a CFD case study of a reacting flow. So this was about a reacting flow modeling. This was an overview, or this was a sort of a fundamental review of the concepts. The summary for this particular webinar is: chemical reactions require additional terms and sets of governing equation, and reaction kinetics can usually be defined, and Arrhenius rate type of mechanisms are used to model reaction kinetics. Mixing effects also have to be incorporated using various models, and reacting flow modeling is nothing but combination of chemistry, chemical kinetics, mass transfer, and fluid mechanics. And presence of turbulence, as always, makes flow analysis much more complex, and we will study details of this in the coming session, part 2 of this particular webinar. As we have come to the end of this webinar presentation. Before we end this particular webinar, I would like to give information about LearnCX as a training provider, and if somebody among you is new to the field of CFD, what sort of skill sets is required in order to get into the field of CFD analysis. And there are some fundamental skill sets like fundamentals of fluid dynamics and thermal science, and fundamentals of CFD, usage of CFD software, how to utilize CFD in design, how to make sense of CFD results. Those sort of aspects are required. And we as a training organization or training provider believe that in order to get all these skill sets and software skill set, it is not always necessary to undergo rigid classroom training, which is having fixed syllabus and limited amount of hours. What we offer at our end is a entirely new training module based totally on internet, which does not require travel. All the training resources are available at your desk. We also provide hard copy of our training material, which will be provided to you within the training material course cost. You can go over the material any number of times, which is pre-recorded sessions. You can also have interactive live sessions with our users through WebEx, and you can get your doubts cleared throughout the course. You have a huge library of lectures for the courses and tutorials, and we also provide training assignments which will be given to you during the course to assess your level of expertise. So all these things provide a very innovative method of CFD training and CAD training, which is given completely online. Currently we have 4 flagship courses, which is CFD modeling using ANSYS ICM CFD and ANSYS Fluent, as well as advanced course on multi-phase flow and heat transfer, and computer aided geometric design course. The information of all these courses is available on our training web portal. There are many more courses which are present, which you can go through our training web portal, as well as new courses will be coming up in the coming months. How to reach us is, if you are interested in any of our training courses, is basically visit our website, which is www.learncx.com, and you can also visit our blog, which is blog.learncx.com. You can also connect to us on Facebook or Twitter, and you can also view some of the sample demo videos on YouTube channel, which is LearnCX. But the best way to ask any of your queries is to info@learncx.com. So here you can our technical as well as non-technical doubts will be resolved by just an email to info@learncx.com. So this is the way to reach us. Now we are at the end of this particular session, and we would like to take any questions. If you have, you can put them in the drop box, and we'll try to answer them as much as we can in this session. If you have any more questions, you can always email us to our email address, that is info@learncx.com. So thank you for attending this particular session. We will have part 2 of this webinar, and which will be announced in the coming weeks, and we look forward to you attending that as well, where we'll go much more detail into modeling aspects of reacting flow, and some of the case studies will be presented. So thank you for attending this particular session, and we look forward to your attendance in many of our future webinars as well.